Welcome back. So our first speaker is Oakley from the University of Sheffield. We are very pleased to have him here, and he will talk about Bayesian calibration, history matching, and model discrepancy.
Thank you very much. Thank you for the introduction. Thanks for inviting me to speak. Sort of plan for this talk is, I think I'll first of all just try and spell out exactly the sorts of problems that I'm interested in, with some definitions and notation which are almost the same but slightly different from other people's. Then I'd like to talk about kind of an area that I work in, which is, involves the sort of use of models and uncertainty decision making in sort of health economic applications. And then sort of the main sort of technical stuff, I'm not going to really present anything new. I'd just like to, well, perhaps some people here haven't seen all the details of Bayesian calibration and history matching, so I'll sort of give an outline of both of those and then make a few sort of observations and comparisons between the two. And then finally, just an illustration of history matching on a reasonably sort of large simulator. Okay, so just to sort of set up the problem. So imagine we have some physical process that we are interested in studying, where we get observations from that process that may or may not be observed with noise. So anytime I'm sort of talking about a Z, I'm talking about an observation from a physical process. And then we might take observations at different locations or different experimental settings. And so I'll use T to represent, if you like, inputs, but things that you would know, either just a point in space or time, or a condition for a particular experiment or whatever. So you have these sort of XT observations. And then we have a computer model of that same process. Okay? That I'm going to represent by some function f, and that model will take the same control inputs T, but there'll be additional calibration inputs X that I may not know. So I have to specify those in it as well to run my model. And then we'll get some data from our physical system. So perhaps at different points in time or space, or at different experimental conditions, T, we'll take a measurement and we'll observe Z, possibly with noise. And then two things we might want to do. I might want to calibrate my model to that data. So I might want to find a value of my input X to make the outputs of the model look like those physical observations. And in addition, or alternatively, I may care about sort of making forecasts or predictions. So at new locations, new experimental conditions, I want to predict what the physical process is going to be. Okay. Perhaps directly using the data, but perhaps with a combination of that data and my model. Okay, so this is sort of a slightly different take on some things Danny was talking about yesterday. So I'm going to sort of make a distinction between different types of calibration inputs. So again, we're going to say that in our model we've got control things that I know or can fix, but then even for that calibration input, we might imagine sort of different types. So first of all, we might have what we call a tuning input. And this is something that's just sort of exists in the model, but doesn't necessarily have any sort of real physical meaning. So certainly in that sense, there's no sort of independent true value. There might be perhaps a best value that makes the model perform correctly. But even that's debatable. But certainly we're going to have types of inputs that don't have aren't directly physically observable, might loosely correspond to something in the real world, but don't really have aren't true quantities in any sense. But separately, we might have inputs that really do have sort of real world meaning, and certainly in the sort of areas that I work in, very often these inputs X are physically observable things. And so kind of a way to sort of, if you like, define that is you can imagine that there are experiments that you can do that have nothing to do with that computer model, which in theory you could do an experiment and potentially you could directly learn the value of that X. Okay? So in that sense, there is a true value because you do your separate experiment and you discover what the value of that input would be. Okay, so now I'd just like to sort of talk a little bit about sort of a general application area and the sort of live problem that I'm involved in. So I'm not going to get any results from this, but just to sort of give a little bit of context what sort of things we might be wanting to do with these calibrated models. So in the United Kingdom, we have, as sort of part of how our health system works, we have decisions that are made about whether or not particular drugs are available to the patient population through the NHS, and these decisions are made based on their cost effectiveness. Okay? So when we talk about a technology, we might be talking about a drug, but it could be a medical device, a hearing aid or something like that. It could be a particular surgical procedure. So just because something's licensed doesn't mean that it's necessarily available for you on the NHS. Sometimes it might be available or not on the basis of whether it's judged to be cost effective. And we have this decision-making body, National Institute for Health and Care Excellence, called NICE, who make decisions on whether or not certain technologies are going to be available. Now, when they do this, as far as possible, we'll consider all the treatment, all the costs that will be associated with that treatment, with that technology. So we're not just talking about the price of the drug. If that drug keeps you out of hospital, then that's going to save costs down the line. So that would be incorporated into the total sort of cost of that treatment. So you try and sort of account for all the costs that would be associated with that treatment. And then we try and measure health on a common scale, regardless of what disease area you're looking in. So we've got this unit of measurement of health, the quality adjusted life year. And one QALY is thought of as being 1 year in perfect health. So if you sort of live with a particular condition for a certain number of years, if you're not in perfect health, you might not accumulate the maximum number of QALYs and so on. And then generally the way it works is if you've got a current treatment and you're proposing to use a more expensive but more effective one, broadly that treatment has to cost no more than an extra £20,000 to £30,000 for every extra QALY that it will give you. Okay, so that's kind of a rough threshold on how much we think we can afford to pay for a more effective treatment. Okay, and this sort of process sort of happens quite regularly. So NICE has 4 separate committees, and each committee meets about once a month. And at each meeting, they might look at sort of 2 or 3 decisions. So, in effect, there's sort of these decisions are being made sort of pretty much every week, in a sense, in terms of particular costs. Usually, it's where a drug's been sort of flagged as being particularly expensive, where it would go through this sort of process of evaluation. And kind of important to point out that these decisions, well, say all of us, I mean everybody in the UK at least, whether or not that drug is is going to be used on you or not, the decisions still affect us. Okay, so they're making a decision about a particularly expensive cancer drug, okay, and whether that's going to be available or not. Okay, if they decide that yes, that new drug is good value for money and we're going to start using it, there's no extra money to pay for it. That money comes from elsewhere in your healthcare budget. So this is all about allocating your healthcare budget as effectively as possible so that you can do the most amount to give the most amount of benefit for the most number of patients. So whether or not that particular technology is relevant to you, the decision still affects you because it still affects what resources are going to be available to you for when you need healthcare. So kind of it is a very sort of important decision-making problem. Okay, so kind of another sort of interest here in kind of the relationships between models and decision-making, and there's kind of a nice sort of strong link in this instance. So there'll be some clinical trial data about your new technology and other published evidence, but almost always they will try and extrapolate, predict what those costs and healthcare benefits are going to be beyond duration of any trial that you've got. Okay, so you extrapolate beyond whatever available data you might have, and that extrapolation, that prediction, is based on a computer model. Now, some of these models are very simple. Could just be nothing more than a sort of spreadsheet calculation in Excel. Then we have these sort of Markov cohort models, which are a little bit more complicated. So you have sort of different states that patients might be in at a particular time, and each state might be associated with a sort of a treatment cost and a quality of life, and patients move between the different states, accumulating different costs and qualities as they go on. And then more complex still is you might have these sort of individual patient simulation models that kind of simulate, rather than for a sort of cohort of patients, what happens to an individual patient, perhaps take into account of all their past history. So these things aren't massively computationally expensive, but certainly the sort of individual patient simulation models on a sort of desktop PC might be taking a few minutes per run, so they're not trivial. Okay, and certainly there's no sort of nice closed form expression for the input-output relationship. So we're not dealing with climate models here, but they're not completely trivial either. And this model is going to produce this sort of key output, this cost per quality, and that number that comes out of the model plays a very strong role in determining the final decision. So usually the way it works is that the manufacturer who's made this technology that's being evaluated, they will produce a model, they'll populate it with input values and so on, and they'll come up with an estimate, and then their model and data gets handed over to an expert review group, so an independent academic group who sort of assess it, will raise queries and so on, and then it all comes to a committee where, again, the sort of structure of the model and the data source and the inputs all kind of get picked over. So there'll be some sort of debate about what's gone into the format model, but ultimately the number that comes out of that model is pretty much going to determine whether or not that drug is available in the patient population. So it's kind of direct, there's a very clear link from what comes out of the model and what decision is going to be made. Okay, now NICE is sort of very aware of uncertainty, and so I'll sort of say a few comments about how that's handled. So we'll sort of write the model like this. So imagine that we're now going to have T might be the different decision options that you're looking at, so perhaps one or two settings for T, and then you've got various inputs that you need in your model, so inputs to do with what proportion of patients are going to respond to your particular treatment, what proportion of patients are going to have side effects, how long they're going to spend in hospital and so on. So you've got a whole collection of inputs that you need to sort of populate your model, and those inputs will all be uncertain. And a lot of work goes into quantifying uncertainty about those inputs. So usually there'll be a team of people who will first do a sort of systematic review of literature, and they'll follow quite a strict protocol and try and pull all the evidence that they think is relevant to the effectiveness of all the treatments of the question, and then usually goes through a sort of a fairly sort of heavy Bayesian meta-analysis to come up with sort of input distributions and so on. So there's a considerable amount of effort that goes into quantifying the input uncertainty. Certainly it's a long way from just very crude uniform distributions over arbitrary ranges. Okay? And then NICE have sort of guidelines on how they expect these analyses to be done. So I've changed the wording a little bit. So what they want are distributions, probability distributions on each uncertain input, and they want to see those distributions propagated through the model, so Monte Carlo or whatever. And they kind of like it to be handled that way. I've called it forward propagation of uncertainty. I kind of guess that's probably what people are more familiar with here. NICE themselves actually, and in health economics, is actually referred to as probabilistic sensitivity analysis, but it's not what some of us call sensitivity analysis. But the thing they care about is this basic propagation of uncertainty through the model. Okay. Now, I suspect a lot of this is kind of what they prefer to see is, this is the kind of output that they want. They want to see kind of an average value of that output averaged over the input distribution, as opposed to just plugging in an estimate, a best estimate of your model, and doing a single model run. It's less clear that they're actually that interested in the distribution of the output. So they kind of want uncertainty to be quantified, but I suspect it does really boil down to, what is the mean of that distribution. If it's above some threshold, they'll do one action. If it's below a threshold, they'll do another action. You can present the distribution, but then what do you actually do with it? So most of the time, they kind of want people to be sort of responsible and thinking about input uncertainty, but I suspect ultimately it's primarily the mean that's going to drive things. They also care about model discrepancy, and they recognise that these models are going to have limitations. But here they kind of asked it to be handled in a more sort of scenario sort of analysis type way. So you might present results from a few different structural assumptions to see what happens, and then within the committee meetings they might pick over the assumptions that have been made and sort of make judgments about what they think is most suitable. So they don't kind of expect anything sort of probabilistic at this stage. They're not yet asking for Gaussian processes, but I'm sure that will come. Okay, so now what I'd like to do is just sort of tell you a bit about a kind of live problem that I'm involved with. So this was. So we're not talking about drugs now, but this was an analysis that was done for NICE, and it's mainly Matt Stevenson, who's the modeler, who's sort of leading this, and I contributed a little bit with some of the elicitation that was evolved initially. So this was to do with concerns about spreading the risk of spreading CJD, Creutzfeldt-Jakob disease. So I assume most people know what that is, but it's a fatal neurological disease. Very nasty if you get it, and there's no cure for it. So the origins for this were in the sort of BSE variant CJD sort of outbreak in the 1890s. This is where beef cows were given sort of feed which led to them developing mad cow disease, and then people would eat that contaminated beef. And then there were this sort of outbreak of this variant CJD. So this sort of disease crossed over from animal into humans. And this was sort of in the 1980s and 90s. And there was a concern that you could spread variant CJD via surgery. So you operate on someone who's got the disease. You think you've decontaminated your surgical instrument, but the decontamination doesn't work, and then you operate on another patient, and then you spread that the prions that carry disease from one patient to the next. So this was done in 2006 initially, and at about that time there'd been about 150 known cases of variant CJD. But they also do these appendix studies where they take samples from appendices that have been removed, and they look for traces of the disease-carrying prion there, and that suggests there's a much higher prevalence. So there's a kind of a concern that potentially this disease has a long incubation period, and many more people are possibly carrying the disease-causing prions than you've observed just from the numbers of CJD cases so far. So what we were looking at was whether or not it would be cost effective to switch to using single-use surgical instruments for these particular operations. So instead of trying to decontaminate your instrument, you just throw it away, and then you'll at least guarantee that you're not going to infect anyone if that instrument is infected. Okay. So I just cut this from a report, so don't need to read all the text, but Matt built this individual patient simulation model that simulates patients arriving at a surgical centre, having the operation, then potentially the instrument that you use gets contaminated. You try and decontaminate, but that only has a limited effect, and then that instrument gets potentially used on another patient who may or may not be affected. And this model had, well, there are lots of parameters, but at least 26 uncertain ones to do with the epidemiology, so what proportion of the population are currently infected for different age categories, what's the incubation periods and so on, how effective is the decontaminant at removing prions and so on. So we did quite a big elicitation exercise to come up with input distributions for all the things that we are uncertain about. So based on the numbers that come out of these models, we're going to make a decision. The decision's going to be made on whether or not you'd switch to these single-use surgical instruments. Okay. Now, in terms of sort of the operations that we were looking at, I think it was the order of 2 million of these operations being done every year. So if you just think about what's possible, you can make a very bad decision either way. So on one end of the spectrum, if you do nothing and there's high prevalence and high infectivity and so on, you could actually get a self-sustaining epidemic. So someone is operated on, they contaminate the instrument, that instrument contaminates, infects more patients who then go on to infect more patients and so on. So potentially there's a real sort of health disaster there. But on the other end of the scale, if you're, it's possible that instead you go to this decision to sort of be safe and you switch to these single-use instruments, and then you're spending hundreds of millions of pounds every year, it's the order of £500 million every year, with no benefit. Again, that's not extra money, that's £500 million a year that you've taken out of your healthcare system, and you're not doing any good with it. So that's serious as well. So it's important that we get this decision right. So at the time, the decision was that in pretty much every case that you'd stick with reusable instruments. There are a few exceptions and a few sort of conditions on how things were managed, but primarily the decision was that switching to single use was just not going to be cost effective. You'd be potentially spending hundreds of thousands of pounds for a single quality in a sense. Now we've been so that was back in 2006, and they kept sort of monitoring and doing these sort of prevalent studies since then, and we've now been asked to sort of look again at the guidance. So we've got some new data on epidemiology. There was a new appendix study recently. The single-use instruments have come down in price, and there are also sort of concerns that groups that you thought would be sort of protected from the outbreak may not necessarily be. So there's sort of, as again I said, it's the understanding of epidemiology that's changed a little bit. But now we've got model predictions for everything that's happened since 2006. So now we can do this calibration exercise. So this is a bit odd. The calibration data, strictly, is that we haven't actually observed any infections in that period. So that's kind of already pointing that probably you're not going to change your decision. But it is possible that you're just not detecting these cases. So when we say iatrogenic CJD, that's CJD that as a result of a surgical infection. And then it's possible that you misclassify that as a sporadic case, which is these just things sort of happen naturally, the order of about 100 cases a year or so. And it's also possible, particularly in more elderly patients, that someone who's died from CJD is actually diagnosed as dying from another neurodegenerative disease. Okay? So although there's no observed cases, you can't be certain of this. So what we need to do is think about how we're going to link these observations to our model outputs, calibrate, and then see if the decision is going to change based on other things that have changed up elsewhere. So that's kind of all going on at the moment. So I'm not going to present the results on that, but I might just comment a little bit later on how some of the things I talk about might be relevant to this. Okay, so let's just recap. So we've got our calibration data. So we've got these control inputs and we've got these observations in the physical system. And if we're thinking about this from a sort of Bayesian perspective, we might want to derive a posterior distribution. And if we're forecasting, we might want to sort of integrate out over our uncertainty in those calibration inputs and then run them through the model. Okay? So we've got a likelihood term here, where typically evaluating that, you're going to need to know what your model would do if you were to run it at input x star. Okay? So what outputs would that produce? And if you're dealing with a computationally expensive model, then you might sort of not be able to sort of directly evaluate your model, and you might have to sort of go through an emulator. So I don't know if we've had a picture of an emulator yet this week. So in case you haven't, here's one. So this is just a little toy one-dimensional example. So basically the idea is you would run the model at a certain number of inputs that you can afford to do, and then we kind of use this Gaussian process model where we quantify uncertainty about what the model would do at intervening inputs. So where we've got sort of training runs, our kind of uncertainty grows as we move away and then pinches in again, and then it kind of blows out as we extrapolate. And then if we want, we can do more runs, and then that kind of pins down the function a little bit better, so that we've got relatively low uncertainty even in between our model runs. So that's all kind of done with a Gaussian process model. As you can see, they work fabulously in toy one-dimensional problems like this. Not so good in real problems, but they're kind of manageable. Right, then we've got this problem of model discrepancy, where we don't believe that our computer model is describing the physical system perfectly. And this is kind of what I'm going to be talking about from now on when I talk about the Bayesian calibration approach, where we're going to introduce this extra term. So we're now going to link our model to our observation. So what we say is that what we observe, and sorry, it's a typo, that should be x star. So we're going to imagine there's a single input x star, so that what we observe is our model at some calibration inputs, and then we've got this observation error here, and then we've got this extra term here, which represents this discrepancy. Okay, and it's the bias between the model output and reality. We're not modelling it as a function of x in the sense that we think that in the real world there's just a single x. X doesn't vary, so we could think about what it would be for different x's, but we're not going to explicitly model it as a function of x because in reality x is not changing. And normally that's modelled with a zero mean Gaussian process, so kind of like the pictures that I was showing you a moment ago, but without any sort of prior trend put in. Now no one's really complained about model discrepancy here, which is good, but it doesn't always go down very well with modelers, and I quite like to collect quotes that I hear from either collaborators or elsewhere. So here's a couple. What are you doing? Are you trying to make bad science good? This is terrible. Why are you trying to? What about, you should be putting better physics into your model, not just fudging it with one of these funny normal distributions. Now, there's various things you might say in response to this. Personally, I would suggest, when people talk about this sort of stuff, is that you actually go back and look at the original application in the McKinley and O'Hagan paper. What they were doing, what this was sort of motivated by, was a problem where you've had an accidental release from a nuclear power station. So it's kind of released a plume of radionuclides, and which then get deposited on the ground, and you're needing to respond to that pretty quickly. So within 24 hours or so, and you're sending people out to take physical measurements where they can, and they're telling you what the concentration of your radionuclide is on the ground. You take that data and you calibrate your model to it, and then you predict where you can't take the measurements. Okay, so this is all happening very quickly. You're making you're taking that data, you're calibrating the model, and you're making decisions within the space of 24 hours or whatever. And you're not suddenly going to come up with a better physics model within minutes of seeing that your model's not fitting the data perfectly. So these are things that really operate on completely different processes. Here we're talking about the model that you've got now that you're having to use, and how you might handle the fact that it's not fitting the data perfectly. When you're talking about better physics in your model, you're talking about years of research down the line. So these aren't competing philosophies. They operate on different timescales. This one, I think, is a little bit more valid. That someone said, well, basically, so what you're doing basically is just adding more noise to your data until your model can fit. And that needs a little bit more thought, because I think sometimes that potentially is all we're doing. Okay, so that was basic idea of sort of Bayesian calibration with discrepancy, which is what I'll be sort of talking about from now on. And that's kind of one way that we might go about it. Another way is through history matching, which I don't know if this is the first reference, but it's definitely older than the calibration approach, which is sort of pioneered by Michael's group in Durham. And the emphasis here is literally, in a literal sense, you're trying to throw away regions of input space where you're confident the model can't fit the data. And kind of what you're hoping is that at the end of the process, what you're left with is a smaller part of the space where you do actually see good fits. It's possible that you might throw away all the input space, but I don't think we hope to do that when we set out. We're hoping that at the end of it all, you get some model runs that do actually fit the data. So for the moment, I'll drop the control inputs, but it's broadly the same sort of framework. You've got your physical observation, you've got your model, which you might imagine can be run at some best input value, although again, Danny suggested ways that you might not make that assumption, but for the moment, I imagine they've got a single input value. We've got some discrepancy, and we've got some observation error. Okay. So normally this is, again, in the sort of scenario where you're dealing with a computationally expensive model. So we're going to run the model and build our emulator for F. Now this is kind of has its origins in sort of Bayes linear thinking, so we don't need a distribution for F, we just need moments. Okay, so our emulator is going to give us an expectation and a variance. And then for any candidate input value, we're going to measure this implausibility. So exactly what you calculate will depend a little bit on the sort of the nature of your input and output data, but for the moment, assume we're looking at the scalar output. So we're going to look at the difference between your observation and your emulator mean, and then you've got these three variances. So you've got your variance of your emulator, so your uncertainty about the emulator, variance from the observation error, and your variance from the discrepancy. Okay, and then typically you don't have to do this, but if you see an implausibility greater than 3, that's kind of taken as a threshold, and that's sort of justified by Foucault-Schein's 3 sigma rule, which I think says if you have a unimodal distribution, any unimodal distribution with a finite variance, then 3 sigma will give you plus or minus 95% of the mass. Sometimes you can be a bit more conservative than that, but it's kind of a guide. So you find parts of input space where implausibility is low, and then you rerun your emulator in that part of the space. And then because you've concentrated your points down, your new emulator is likely to have smaller variance over that sort of reduced region. Okay? So you'll find that now when you start trying again, you might get slightly larger implausibility values because you've shrunk this term a little bit. And you can kind of iterate until you don't get anything, any further points to rule out. So this is a toy example. I think I should be thanking Yanis Andrianakis for this, unless he got it from you.
I'll be showing the same one this afternoon.
Okay. So very quickly, here's our emulator. We're trying to sort of calibrate these points. Okay. So we've got parts of the space. So I don't know what the output of my simulator is going to be, but I'm confident it's too far away from that calibration data. So I would kind of rule out this part of the space as implausible. Same over here. Again, I don't know what that output's going to be, but I know it's not going to be sufficiently close to my target data. Here I'm not sure what's going to happen yet, so what I would do is I'll do another run, and that tightens up the uncertainty down there. So again, I've got parts of the space where I think I might get a match, but I've got some more points there that I've excluded. So you kind of focus in on where you think you're going to find these matches. Okay, and then there's sort of hybrid approaches where certainly when you sort of discard parts of the space, it makes your emulation problem easier. So what some of us have done is kind of try to sort of use these ideas, but more in a sort of a likelihood framework. So we're going to go at sort of emulating a likelihood and then sort of sampling from the posterior with important sampling. Rich Wilkinson has sort of tried similar things to sort of use emulators to speed up ABC, again kind of iteratively throwing away parts of the space. And Just for a little bit more on calibration with ABC, there's a kind of a paper that mainly TJ did that some of us were sort of contributing to, that looking at sort of ABC in comparison with history matching again for sort of calibration. Okay, so I'm going to have to put that again at the end. And then, so that was looking at, that was all presented in the univariate case. If you're dealing with multiple inputs, so let's say we've got a 2-input problem. This is actually for the likelihood version, but it's kind of the same idea if you're doing sort of implausibility. So you start with a set of runs over the input space, and what we're going to do is divide the space up into these bins. So I've now got my first input kind of fixed in this region, and my second input is varying. And then I would look for, within each bin, either my minimum observed plausibility or my maximum likelihood. So I look for the best fit inside each bin, okay? And then I would take that best fit value, and then if I can see bins where that best fit is very bad compared to other places, or in absolute sense if it's with implausibility, then I can throw that part of the space away, okay? Okay, so that's kind of give you an idea of Bayesian calibration and an idea of history matching. Let's have a fight between the two, okay? So from my own experience and from seeing particularly what the Darwin group has been doing, seems to me that if you are trying to just find fits to the data, it just seems to work better and easier with history matching than it does going straight off with a full calibration. So if you're just trying to find fits to your data, my preference will always be to start with a history matching. And this is something that Michael said, so I'll just comment on this in a moment. Possibly the reason for this, one of the reasons for this, is that with history matching you don't explicitly have to try and fit everything in one go. Okay? So this is just a very sort of noddy illustration. This might be a very obvious point, but I think it's worth just spelling this out. Let's suppose I've got a model that produces 2 outputs, and I've got 2 calibration outputs I'm trying to tune my model to. Okay? So just so I can plot it, I'm going to imagine it's a model with 2 inputs that produces 2 outputs. I'm going to have a vector of discrepancies and a vector of errors. Okay? And let's suppose that I'm going to try and match for both of those outputs simultaneously. So maybe to do that, I've got to land both my inputs in some very small region of the input space. Okay? And to start off with, at least, I think I need to be exploring everywhere to make sure that I'm not missing any matches. And I've certainly been involved in a problem where, looking at the likelihood really is very flat until you start hitting the kind of concentration here. So when you sort of do runs out here, you see you don't get a match, but you've kind of got a very little idea of where you need to go next. So you kind of very difficult sometimes to get started. So with history matching, what you might do is rather than trying to match both those outputs simultaneously, you might just pick one output, okay? Again, it's just a little notional illustration. So if you're just trying to match one output, that's going to give you a bigger region, input region to find out. It won't necessarily look like this. It might be a diagonal strip or some other sort of region of space, but almost certainly it's going to be a larger space that you're trying to find if you're only trying to match the one output, okay? Oh, again, just a kind of notional idea. Let's imagine it's 200 runs, okay? So 200 runs and I don't get any hits, okay? So I might do 100 runs, but now I'm only trying to match the one output, so it's easier to find hits, and I get a few hits here, okay? And I can also see that if I push X1 outside this range, I don't get any matches at all. So I've matched that first output, and I think I know what I need to do to be matching to that first output, and then I match the second output, so I'm now going to keep X1 fixed, and I'll do another 100 or so, but now I start getting the hits, okay? So it's kind of exactly as Michael said, if you try and match everything at once, it's potentially very difficult, but with history matching, it's easy just to match things sequentially, so that each stage, it's easier to do, okay? And my guess would be, this I think is for me, I think it's perhaps the primary reason why history matching is easier than the Bayesian calibration.
I totally agree with everything you said, which is all good. There's just the additional issue of that there are some outputs that are easy to emulate.
Yeah.
Your idea there is very good, and it talks about the geometry of the situation. There's also the fact that certain outputs you look at can be very easy to emulate in wave one, and other ones can be a nightmare. Once you've constrained to this sort of picture, then other outputs become easy to emulate. So it's that emulation difficulty which also strengthens this.
Now I was thinking about this yesterday, so this slide might be wrong, but I did wonder, well, supposing you tried to do the same thing in a sort of fully Bayesian sense, you could also try to do things sequentially, but that might be harder. So let's suppose you're trying to calibrate to two observations, okay? So if you try and hit everything at once, you're going to need to think about this full likelihood function for a given input, the distribution of both outputs. But you could apply Bayes theorem sequentially. So perhaps you just calibrate to the first input, okay, which is going to be easier. And then once you've kind of worked out, or perhaps got a sample from that calibrated distribution of the first input, then you calibrate to the second. But it's possible that this is going to get trickier because this term here is going to relate to what your computer model is going to do if you run it at a particular input and you already know what one of the outputs is. Okay? So I suspect if you're going to do that, you need to be thinking about a multivariate emulation so that you can handle the correlation between the outputs. So you could try a sort of sequential, fully Bayesian approach, but I think it would be much more difficult. Why bother? Another issue is this difference between distinction between absolute and relative fit. So when you're working with implausibility, it's quite a nice, easy to interpret measure of fit, and you know what you need to be excluding. Okay? If you're doing things with likelihood, you get a relative measure of fit, so you can kind of see if something's bad, but it's hard to know if you've necessarily found something good or not. So when you kind of do these sorts of implausibility plots, so this is looking at pairwise inputs, so you just take let's just take a pair of these two inputs here. We get a region here with implausibility of 3 or higher, so you kind of know you're not going to get any good fits here. We get implausibilities down, sort of 2 to 0, lower down, so you understand what's going on there. If you do it with kind of likelihood, you can kind of see that you get regions with high likelihood, regions with much lower likelihood that you can exclude, but you don't necessarily know that, you can still be quite a long way off from fitting the data here. It's harder to know kind of how far down you should go. So you can do it, but it's not as straightforward as it is in the likelihood approach. Okay, and then finally I want to talk about what happens when you try and do this, trying to learn real world inputs. Danny gave this example yesterday, and I've also been sort of looking at it a little bit, so just wanted to expand on it a little bit. So this is a paper by Brynjar and O'Hagan, and they were looking at the sort of Kennedy and O'Hagan calibration model where you're trying to learn true input. The example from the paper is that I didn't fully understand the intuition of it, but if you don't worry about that, basic scenario is you've got a simulator that has a true input value. When you plug your true input value into your simulator, you get this straight line here. Okay, so we're just going to suppose that this x star, you really care about it, it's got a particular number, and when you plug it into your model, you get some output that looks like this. The simulator doesn't model reality perfectly, so when you do your physical experiment, you get some observations here. So you kind of get this bias in your model. And then first thing they do is just derive the posterior ignoring discrepancy, and if you do that, you get this terrible result where you get your posterior distribution. You're very certain you know what this input is, and you're wrong because the true value is over here. So without accounting for discrepancy, you get this really nasty result. And then what they do is they say, well, what happens if you just apply the basic model for discrepancy? So we're going to have a discrepancy process delta with a sort of zero mean Gaussian process. So we've got this parameter sigma squared that's describing sort of magnitude of discrepancy for any inputs, and parameter lambda that describes sort of the smoothness in that discrepancy, or the smoothness in the real world once you've taken away the model. And they treat those as uncertain, and then you sort of run that through, and that just about manages. Okay, so now we've got a posterior. It's still kind of peaked clearly around the wrong values. So there's kind of some bias there in a sense, but it's just about picking up the right value. And they sort of go on to look at putting more structure into the discrepancy to correct it. So my Durham friends might say, well, why don't you try history matching instead? So let's try that and see what happens. The one-dimensional case is not that relevant, but it's helpful just to sort of understand a little bit about how you deal with multivariate output. So we've got a single input, and our model produces these 31 output values, okay, because I've got these 31 observations. Different types of implausibility that you might try. So kind of the simplest that you might consider, this is quite often used, is that you take just the maximum implausibility for each individual output value. So you look at where is your prediction worst, okay? So what's the worst it can be, and if the worst prediction is bad, then you would reject that as an input, okay? So in this example, we've got a very fast function, so we're not going to have the emulator, so I'm just going to replace that expectation of the function by its true value, and that variance term will be 0. But I've got still noise, variance from the noise and variance from the discrepancy. And I'm going to pull out the same variances that you had for that Gaussian process model, okay? So you get sort of a picture that looks like this. So if you're using 3 or even a more aggressive cutoff, you still kind of pick up the right value, but I mean that's still a little bit arbitrary, but just to show you what happens. But a bit more interesting is to think about perhaps a more appropriate multivariate implausibility. So in that Gaussian process model, we've got this correlation between discrepancies at different control inputs. So you're in a particular part of the design space, you see that you've got an error, and you think that your error nearby is going to be similar in your model prediction. So you might instead, so let's have a vector of all my outputs, model outputs, a vector of my observations and so on, and an appropriate variance covariance matrix. And you might instead use that as an implausibility function. If you look at Ian Michael's galaxy formation paper, this is, I think, what's done, and they carefully went through with their modelers and thought about what are the variances and covariances that should go into that thing. So it's quite a hard elicitation exercise, but can be done. Okay. And then, so I'm going to try this. So I need a correlation parameter. So I'm going to use the expected value that was assumed in the prior for the Gaussian process discrepancy model. And this is kind of a bit more interesting because the implausibility is kind of, so this is at the true value, and it's not quite so far off, I think sort of leveling out, not so far off the true value here. I had to go and ask Ian yesterday what threshold you should be using for this, because it's not that free business anymore. And he explained to me that if you're going to do this, then you might have to make some sort of distributional assumption. So you might assume normality, and you've got a chi-squared, and you can kind of put in the threshold. So that's kind of based on a sort of chi-squared assumption. I pull out a high percentile, and that kind of gives me an idea of what sort of cutoff I should be using. So kind of it's interesting, I think, to think a little bit more about what's going on here, and it's kind of important to realise that there's a bit more going on in that full Bayesian modelling. So go back to the fully Bayesian calibration model. We've got this Gaussian process for this discrepancy, and what you have to remember is that in the Bayesian calibration model, you're not just trying to learn x star, your input, you're also trying to learn that sigma squared parameter, okay? And you've kind of got this hierarchical structure. So lambda's talking about correlations. You think of it as correlations at points close by. So I'm at a particular point in the design space, I see my model error, and I expect if I move along a little bit, that model error is going to be quite similar. The way to think about sigma squared is I'm in a particular point in the design space, and I see how well my model's performing. And if I move kind of somewhere else, well, I don't have to worry about the correlation. I'm still think that's informative about what model error I'm going to see here. Okay? And arguably that's not a very good assumption. And again, Danny was talking about it yesterday, where you've got models that you might believe can do certain things well in parts of the space and other things badly in other parts. But you've kind of got this hierarchical assumption here, where you're sort of assuming it's the same. And turns out that it's because you're trying to learn that discrepancy, the consequence of that is it can actually make you less uncertain about that calibration inputs. Okay? So here's my prior distribution for that sigma squared. So that's prior distribution on the magnitude of the discrepancy, if you like. And then the histogram is pulled downwards a little bit. So I think my prior expectation was about 0.09. So in trying to calibrate that model, I've ended up thinking that actually the model can fit the data quite well, and the discrepancy's a bit smaller than I was expecting, and that kind of pulls me into a slightly tighter posterior. So that's the one I had before. That's my posterior distribution where I just do the normal sort of fully Bayesian inference, okay? But if I decide that I'm not going to have that hierarchical assumption on the discrepancy and I just think directly what's my variance, then I get a slightly flatter looking posterior. So it's a bit strange that in attempting to discover that, learn about that variance parameter, I become more certain about the calibration inputs. Okay. Right. One final comment. I'll stop before the end. I won't do the last topic. So when we're dealing with sort of parameter inference, we've got to think carefully about these discrepancies in our calibration inputs and the dependencies between them. Something that I think could be done, but doesn't appear to be done at the moment, is that when we're forecasting, really we need to be thinking about dependencies between discrepancies in both the calibration outputs in our data and whatever outputs we're intending to forecast as well. And I think if we don't, then it potentially becomes a bit less convincing. So if we just talk about parameter inference, so imagine I've got a single output that I'm trying to hit. I've tried some input values. The corresponding outputs are within the noise. So at the moment, this is just experimental. They're just observational noise and no discrepancy. And I find some inputs that I think are hitting, and I maybe put a distribution around them or something like that. And the effect of allowing for discrepancy is that effectively it's inflating the noise so that I have a bit more uncertainty about what the input is. I think that's absolutely fine, because you're saying, if this X star is physically meaningful, what I'm saying is I don't believe that at the true value I will necessarily get as close as I'm expecting to the true output, so I shouldn't exclude that, and that's kind of okay. But forecasting is potentially a bit odd. So again, without any discrepancy at the moment, I've calibrated that output, I've got some model runs that are close enough to the experiment, so that give me the experimental noise, and then I run my model for through to my forecast output, and I get some corresponding output values here. Okay? And then I might not choose to entirely believe what comes out of the model, so I might add some discrepancy on top of each of these points, and that's all fine. But if I just then incorporate discrepancy, and I don't think about the relationship between these errors, then I think it gets a bit odd, because now what you're saying is I should also pay attention to this output here, because when I run that model, I get an output which isn't actually that close to the observation. It kind of seems to me like a bit of a funny argument to incorporate that output value in my sort of forecast set if I've not thought carefully about what's the relationship between the discrepancies between errors in the calibration outputs and in the forecast outputs as well. Okay, and then just a sort of final remarks. So Bayesian calibration, we get a posterior distribution of the inputs and model forecast outputs. With history matching, we're just getting the set of non-implausible sample of non-implausible inputs, and hopefully these model runs that fit the data tolerably well. And I think if you're at the exploratory stage, I think this is absolutely fine, and there's probably a lot of value in agonising over getting a tightly refined posterior distribution. But for decision making, this may not be enough. If you're lucky, then all the non-implausible runs point to the same decision. But if they're not, then I think you've really got to sort of bite the bullet and try and get at the posterior. But even then, history matching is going to be a helpful way to find it. So I was going to give an example, but I think I will stop there. But as a reference, if you want to see some recent history matching in action. Okay, thanks very much.
So I want to go back to your nice discussion. So in fact, a lot of the decisions about warning drugs are taken by these local health commissioners, and I'm slightly worried that in calibrating these models, there's no counterfactual in the sense that you don't know how many people died because they were not allowed to issue with the right drug. So a lot of the reality actually takes place at the local level rather than a NICE level.
That's not supposed to happen, because the whole point of NICE was supposed to end this postcode lottery where things are taken at the local level. And in the NHS constitution, it says that if NICE have approved the drug, you are supposed to get it, regardless of. It may not happen, but
it doesn't happen, and they're even stopping people getting drugs. For example, obese people are being denied treatment all over the country because for certain local, because they run out of money locally.
Oh yeah, sure, yeah.
So I'm just suggesting you try and extend the calibration to local level. What actually happens at that local level?
Yes, I mean
where the people are.
I mean calibration is actually quite rare in these things because mostly it's just a kind of forward propagation. But yeah, I don't know how we do that particular problem, but yes, it's a fair point.
I was interested in the cross-infection problem. Okay, so you look at the prevalence of CJD.
Oh yes.
Yeah. Okay, so you're saying that that's the only thing that could cross-infect? I mean, because are there not other things that could cross-infect as well?
It's possible. The variant CJD, it's called the PRAN, is very resistant to decontamination in a way that other things are less so. So, yeah, it's possible. It's possible that other things.
That's the one that people know about because they've seen it on TV. But I mean, until you test everything. So I'm just saying that there are, in terms of it's like the model discrepancy. There's potential other things which you just haven't put on the table. So in a sense you may be underestimating benefits, and you need to estimate how you're underestimating benefits.
Oh yeah, no, that's absolutely right. And with all these things, there are potentially things that you have not modelled that could. I mean, in practice, what happens is when they do these analyses, they're very strict on the scope, and they say this is what you will look at.
But so the part of the thing about model discrepancy is some of it is not observable because you do not know how many people, in your forward look actually were contaminated by stuff that wasn't in your. Yeah. And at the same time, I also wonder whether your qualies are really a utility. Why are you just interested in the expectation if qualies are not a utility measure?
So qualies are sort of. There's different ways that people list at qualities. One of them is directly as a utility, and the other one's not quite. I think they're as good as utilities, and I think actually basing things on the expectation is reasonable because these decisions are made.
One last question: that everybody has the same value for these things.
But the decisions are made. No, we don't expect everyone to have the same quality, but the decisions are made at a population level, and. In a sense, you're looking at the overall population health benefit.
Okay, so do we have any further questions? No, then